let's connect all of this thermodynamics business to the understanding of equilibrium that we've been developing all semester long. Are you ready? I'm ready. When the components of a chemical reaction are mixed, they will proceed to the equilibrium position. By definition, this is where the rate of the forward reaction is equal to the rate of the reverse reaction. As a result, the concentrations of all reaction species stop changing and remain constant. If you want to determine how long it takes to get a reaction to its equilibrium position, well, that's the realm of kinetics. But if you want to understand equilibrium from a thermodynamic perspective, consider it as a set of concentrations of reactants and products that will have the lowest possible total free energy available to the system. At equilibrium, the free energy is at its lowest state, so the change in free energy of the system from then on is zero. If we take the equation we used in the last video, relating the free energy change for non-standard conditions to the standard free energy change, we can substitute in a zero for delta G because it's at equilibrium, and the equilibrium constant K for Q because it's at equilibrium, and we'll get this equation here. Standard delta G is equal to negative RT natural log K. That's a pretty important equation, and you can tell it's important because it's really big. So why is it so important? It shows us the connection between the equilibrium constant K and the free energy change delta G. From the definition of Gibbs free energy, we've got a connection between equilibrium constants and the second law of thermodynamics. Let me illustrate. If standard delta G is equal to 0, we know that the system is at equilibrium when all the reactants and products are at 1 atmosphere or 1 molar concentrations. That's when Q is equal to 1. So Q is equal to K. So K is equal to 1. Neither the reactants or the products are favored more than the other. But if standard delta G is less than 0, we know that if the pressures and concentrations are all 1, then the system isn't at equilibrium yet, and that the equilibrium position lies to the right, because Q is less than K. So K is greater than 1. The forward reaction to make the products is thermodynamically favored. But if the standard delta G is greater than 0, we know that if the pressures and concentrations are all 1, then the system is past equilibrium, and that the equilibrium position lies to the left, because Q is greater than K. So, K is less than 1. The reverse reaction to make the reactants is the thermodynamically favored one. So here's something else we can do with this equation that relates to standard free energy change with the equilibrium constant. We can calculate an equilibrium constant from thermodynamic quantities. So let's look at this rusting of iron reaction and determine an equilibrium constant from the given enthalpies and entropies. Using the sum of the products minus the sum of the reactants equations for both delta H and for delta S, we end up with these results. If we substitute delta HT and delta S into the free energy equation, we get negative 1,490,000 joules per mole of reaction. This tells us that rusting iron is thermodynamically favored at 25 degrees Celsius. Now let's take the free energy equilibrium constant relationship and solve it for K. Dividing both sides by negative R and T will give us this expression. Taking E and raising it to both sides of the equation will let us solve for K, giving us K is equal to E raised to the negative delta G divided by R and by T. Substituting the delta G, R, and T from the previous slide will show us that K, the equilibrium constant, is equal to E to the 601st power. That's approximately 10 to the 261st power. That's big. I guess the universe really likes to rust iron. It isn't exceptionally fast according to the kinetics, but it is definitely going to happen. I guess we'll just have to deal with it. One reason to study chemistry is because it's awesome. Another reason to study chemistry is to figure out how to use chemical processes to do useful things like work. The sign of delta G can help you predict whether or not a process is thermodynamically favored at a given temperature. The magnitude of delta G can help you predict how much work can be done by a certain thermodynamically favored process. At constant temperature and pressure, the maximum work that could be done by a process is equal to the free energy change for a thermodynamically favored process, a negative delta G. And for a non-favorable process, the free energy change is how much energy would be required to force the reaction. The reason it is only the maximum possible work that could be done is because some energy will always be wasted to do other non-useful things, like overcoming friction and heating up the air around it. The significance of that last statement is a little depressing, so don't think about it too much. But it means that because of the first law of thermodynamics, the total amount of energy in the universe is constant. But because of the second law of thermodynamics, that energy in the universe is becoming less and less useful all the time. So here's a picture of a puppy to make it all better. Remember, this puppy wouldn't exist if it weren't for the second law of thermodynamics.